Phoenix was a robotic spacecraft on a space exploration mission on Mars under the Mars Scout program. A Phoenix lander descended on Mars on May 25, 2008. Mission scientists used instruments aboard the lander to search for environments suitable for microbial life on Mars, and to research the history of water there. The total mission cost was estimated to be about $386 million, which includes cost of the launch. The multi-agency program was headed by the Lunar and Planetary Laboratory at the University of Arizona, under the direction of NASA's Jet Propulsion Laboratory. The program was a partnership of universities in the United States, Canada, Switzerland, Denmark, Germany, the United Kingdom, NASA, the Canadian Space Agency, the Finnish Meteorological Institute, Lockheed Martin Space Systems, MacDonald Dettwiler Associates and other aerospace companies. It was the first mission to Mars led by a public university in NASA history. It was led directly from the University of Arizona's campus in Tucson, with project management at the Jet Propulsion Laboratory in Pasadena, California, and project development at Lockheed Martin in Denver, Colorado. The operational funding for the mission extended through November 10, 2008. Phoenix was NASA's sixth successful landing out of 7 attempts and was the first successful landing in a Martian polar region. The lander completed its mission in August 2008, and made a last brief communication with Earth on November 2 as available solar power dropped with the Martian winter. The mission was declared concluded on November 10, 2008, after engineers were unable to recontact the craft. After unsuccessful attempts to contact the lander by the Mars Odyssey orbiter up to and past the Martian summer solstice on May 12, 2010, JPL declared the lander to be dead. The program was considered a success because it completed all planned science experiments and observations. Program overview. The mission had 2 goals. One was to study the geologic history of water, the key to unlocking the story of past climate change. The second was to evaluate past or potential planetary habitability in the ice-soil boundary. Phoenix's instruments were suitable for uncovering information on the geological and possibly biological history of the Martian Arctic. Phoenix was the first mission to return data from either of the poles, and contributed to NASA's main strategy for Mars exploration, follow the water. The primary mission was anticipated to last 90 sols just over 92 Earth days. However, the craft exceeded its expected operational lifetime by a little over 2 months before succumbing to the increasing cold and dark of an advancing Martian winter. Researchers had hoped that the lander would survive into the Martian winter so that it could witness polar ice developing around it. Perhaps up to 1 meter of solid carbon dioxide ice could have appeared. Even had it survived some of the winter, the intense cold would have prevented it from lasting all the way through. The mission was chosen to be a fixed lander rather than a rover because costs were reduced through reuse of earlier equipment. The area of Mars where Phoenix landed is thought to be relatively uniform and thus traveling is of less value. And, the equipment weight that would be required to allow Phoenix to travel can instead be dedicated to more and better scientific instruments. The 2003–2004 observations of methane gas on Mars were made remotely by 3 teams working with separate data. If the methane is truly present in the atmosphere of Mars, then something must be producing it on the planet now, because the gas is broken down by radiation on Mars within 300 years, therefore the importance to search for biological potential or habitability of the Martian Arctic's soils. Methane could also be the product of a geochemical process or the result of volcanic or hydrothermal activity. Other future missions may enable us to discover whether life does indeed exist on Mars today. History of the program. While the proposal for Phoenix was being written, the Mars Odyssey orbiter used its gamma-ray spectrometer and found the distinctive signature of hydrogen on some areas of the Martian surface, and the only plausible source of hydrogen on Mars would be water in the form of ice, frozen below the surface. The mission was therefore funded on the expectation that Phoenix would find water ice on the Arctic plains of Mars. In August 2003 NASA selected the University of Arizona Phoenix mission for launch in 2007. It was hoped this would be the first in a new line of smaller, low-cost, Scout missions in the agency's Exploration of Mars program. The selection was the result of an intense 2-year competition with proposals from other institutions. The $325 million NASA award is more than 6 times larger than any other single research grant in University of Arizona history. Peter H. Smith of the University of Arizona Lunar and Planetary Laboratory, as principal investigator, along with 24 co-investigators, was selected to lead the mission. The mission was named after the phoenix, a mythological bird that is repeatedly reborn from its own ashes. The Phoenix spacecraft contains several previously built components. The lander used for the 2007 Euro-08 mission is the modified Mars Surveyor 2001 lander, along with several of the instruments from both that and the previous unsuccessful Mars Polar Lander mission. Lockheed Martin, which built the lander, had kept the nearly complete lander in an environmentally controlled clean room from 2001 until the mission was funded by the NASA Scout program. Phoenix was a partnership of universities, NASA centers, and the aerospace industry. The science instruments and operations were a University of Arizona responsibility. NASA's Jet Propulsion Laboratory in Pasadena, California, managed the project and provided mission design and control. Lockheed Martin Space Systems, Denver, Colorado, built and tested the spacecraft. The Canadian Space Agency provided a meteorological station, including an innovative laser-based atmospheric sensor. The co-investigator institutions included Malin Space Science Systems, Max Planck Institute for Solar System Research, NASA Ames Research Center, NASA Johnson Space Center, MDA, Optech Incorporated, SETI Institute, Texas A&M University, Tufts University, University of Colorado, University of Copenhagen, University of Michigan, University of Neuchâtel, University of Texas at Dallas, University of Washington, Washington University in St. Louis, and York University. Scientists from Imperial College London and the University of Bristol provided hardware for the mission and were part of the team operating the Microscope station. On June 2, 2005, following a critical review of the project's planning progress and preliminary design, NASA approved the mission to proceed as planned. The purpose of the review was to confirm NASA's confidence in the mission. Specifications: mass, 350 kg, dimensions, about 5.5 am long with the solar panels deployed. The science deck by itself is about 1.5 am in diameter. From the ground to the top of the MET mast, the lander measures about 2.2 am tall. Communications: X-band throughout the cruise phase of the mission and for its initial communication after separating from the third stage of the launch vehicle. UHF links, relayed through Mars orbiters during the entry, descent and landing phase and while operating on the surface of Mars. The UHF system on Phoenix is compatible with relay capabilities of NASA Euro-1 registered trademark S-Mars Odyssey, Mars Reconnaissance Orbiter and with the European Space Agency Euro-1 registered trademark S-Mars Express. The interconnections use the Proximity 1 protocol. Power is generated using 2 gallium arsenide solar array panels, mounted to the cruise stage during cruise, and via 2 gallium arsenide solar array panels, deployed from the lander after touchdown on the Martian surface. NIH-2 battery with a capacity of 16 Ah. Lander systems include a Radian 6000-based computer system for commanding the spacecraft and handling data. Other parts of the lander are an electrical system containing solar arrays and batteries, a guidance system to land the spacecraft, 8 1.0-pound force and 5.0-pound force monopropellant hydrazine engines built by Aerojet Redmond operations for the cruise phase, 12 68.0-pound force Aerojet monopropellant hydrazine thrusters to land the Phoenix, mechanical and structural elements, and a heater system to ensure the spacecraft does not get too cold. Launch: Phoenix was launched on August 4, 2007, at 5:26 and 34 seconds AM EDT on a Delta 7925 launch vehicle from Pad 17A of the Cape Canaveral Air Force Station. The launch was nominal with no significant anomalies. A Phoenix lander was placed on a trajectory of such precision that its first trajectory course correction burn, performed on August 10, 2007 at 7:30 a.m. EDT, was only 18 AMS. The launch took place during a launch window extending from August 3, 2007 to August 24, 2007. Due to the small launch window, the rescheduled launch of the Dawn mission had to stand down and was launched after Phoenix in September. The Delta 7925 was chosen due to its successful launch history, which includes launches of the Spirit and Opportunity Mars exploration rovers in 2003 and Mars Pathfinder in 1996. A noctilucent cloud was created by the exhaust gas from the Delta II 7925 rocket used to launch Phoenix. The colors in the cloud formed from the prism-like effect of the ice particles present in the exhaust trail. Landing. The Jet Propulsion Laboratory made adjustments to the orbits of its two active satellites around Mars, Mars Reconnaissance Orbiter and Mars Odyssey, and the European Space Agency similarly adjusted the orbit of its Mars Express spacecraft to be in the right place on May 25, 2008 to observe Phoenix as it entered the atmosphere and then landed on the surface. This information helps designers to improve future landers. The projected landing area was an ellipse 100 km by 20 km covering terrain which has been informally named Green Valley, and contains the largest concentration of water ice outside of the poles. Phoenix entered the Martian atmosphere at nearly 21,000 km per hour, and within 7 minutes had decreased its speed to 8 km per hour before touching down on the surface. Confirmation of atmospheric entry was received at 4:46 p.m. PDT. Radio signals received at 4:53 and 44 seconds p.m. PDT confirmed that Phoenix had survived its difficult descent and landed 15 minutes earlier, thus completing a 680 million km flight from Earth. For unknown reasons, the parachute was deployed about 7 seconds later than expected, leading to a landing position some 25 28 km long, near the edge of the predicted 99% landing ellipse. Mars Reconnaissance Orbiter's high-resolution imaging science experiment camera photographed Phoenix suspended from its parachute during its descent through the Martian atmosphere. This marks the first time ever one spacecraft has photographed another in the act of landing on a planet. The same camera also imaged Phoenix on the surface with enough resolution to distinguish the lander and its two solar cell arrays. Ground controllers used Doppler tracking data from Odyssey and Mars Reconnaissance Orbiter to determine the lander's precise location as 68.218830 a degree N 234.250778 a degree A/68.218830. 234.250778. Phoenix landed in the Green Valley of Vastitas Borealis on May 25, 2008, in the late Martian Northern Hemisphere spring, where the Sun shone on its solar panels the whole Martian day. By the Martian Northern Summer Solstice, the Sun appeared at its maximum elevation of 47.0 degrees. Phoenix experienced its first sunset at the start of September 2008. The landing was made on a flat surface, with the lander reporting only 0.3 degrees of tilt. Just before landing, the craft used its thrusters to orient its solar panels along an east-west axis to maximize power generation. The lander waited 15 minutes before opening its solar panels, to allow dust to settle. The first images from the lander became available around 7 p.m. PDT. The images show a surface strewn with pebbles and incised with small troughs into polygons about 5 m across and 10 cm high, with the expected absence of large rocks and hills. Like the 1970s-era Viking spacecraft, Phoenix used rocket motors for its final descent. Experiments conducted by Nilton Reno, mission co-investigator from the University of Michigan, and his students have investigated how much surface dust would be kicked up on landing. Researchers at Tufts University, led by co-investigator Sam Konaves, conducted additional in-depth experiments to identify the extent of the ammonia contamination from the hydrazine propellant and its possible effects on the chemistry experiments. In 2007, a report to the American Astronomical Society by Washington State University professor Dirk Schulze suggested that Mars might harbor peroxide-based life forms which the Viking landers failed to detect because of the unexpected chemistry. The hypothesis was proposed long after any modifications to Phoenix could be made. One of the Phoenix mission investigators, NASA astrobiologist Chris McKay, stated that the report piqued his interest, and that ways to test the hypothesis with Phoenix's instruments would be sought. Surface mission, communications from the surface. The robotic arm's first movement was delayed by 1 day when, on May 27, 2008, commands from Earth were not relayed to the Phoenix lander on Mars. The commands went to NASA's Mars Reconnaissance Orbiter as planned, but the orbiter's Electro-UHF radio system for relaying commands to Phoenix temporarily shut off. Without new commands, the lander instead carried out a set of activity commands sent May 26 as a backup. On May 27 the Mars Reconnaissance Orbiter relayed images and other information from those activities back to Earth. The robotic arm was a critical part of the Phoenix Mars mission. On May 28, scientists leading the mission sent commands to unstow its robotic arm and take more images of its landing site. The images revealed that the spacecraft landed where it had access to, digging down a polygon across the trough and digging into its center. The polygonal cracking in this area had previously been observed from orbit, and is similar to patterns seen in permafrost areas in polar and high-altitude regions of Earth. A likely formation mechanism is that permafrost ice contracts when the temperature decreases, creating a polygonal pattern of cracks, which are then filled by loose soil falling in from above. When the temperature increases and the ice expands back to its former volume, it thus cannot assume its former shape, but is forced to buckle upwards. The lander's robotic arm touched soil on the red planet for the first time on May 31, 2008. It scooped dirt and started sampling the Martian soil for ice after days of testing. Phoenix's robotic arm camera took an image underneath the lander on Sol 5 that shows patches of a smooth bright surface uncovered when thruster exhaust blew off overlying loose soil. It was later shown to be ice. Ray Arvidson of Washington University in St. Louis said, "We could very well be seeing rock, or we could be seeing exposed ice in the retro-rocket blast zone." Presence of shallow subsurface water ice. On June 19, 2008, NASA announced that dice-sized clumps of bright material in the Dodo Goldilocks trench dug by the robotic arm had vaporized over the course of 4 days, strongly implying that they were composed of water ice which sublimated following exposure. While dry ice also sublimates, under the conditions present it would do so at a rate much faster than observed. On July 31, 2008, NASA announced that Phoenix confirmed the presence of water ice on Mars, as predicted in 2002 by the Mars Odyssey orbiter. During the initial heating cycle of a new sample, TEGA's mass spectrometer detected water vapor when the sample temperature reached 0 degrees Celsius. Liquid water cannot exist on the surface of Mars with its present low atmospheric pressure, except at the lowest elevations for short periods. With Phoenix in good working order, NASA announced operational funding through September 30, 2008. The science team worked to determine whether the water ice ever thaws enough to be available for life processes and if carbon-containing chemicals and other raw materials for life are present. Additionally, during 2008 and early 2009 a debate emerged within NASA over the presence of blobs which appeared on photos of the vehicle's landing struts, which have been variously described as being either water droplets or clumps of frost. Due to the lack of consensus within the Phoenix Science Project, the issue had not been raised in any NASA news conferences. One scientist believed that the lander's thrusters splashed a pocket of brine from just below the Martian surface onto the landing strut during the vehicle's landing. The salts would then have absorbed water vapor from the air, which would have explained how they appeared to grow in size during the first 44 Martian days before slowly evaporating as Mars temperature dropped. Wet chemistry. On June 24, 2008, NASA's scientists launched a major series of tests. The robotic arm scooped up more soil and delivered it to 3 different onboard analyzers, an oven that baked it and tested the emitted gases, a microscopic imager, and a wet chemistry lab. The lander's robotic arm scoop was positioned over the wet chemistry lab delivery funnel on Sol 29. the soil was transferred to the instrument on Sol 30, and Phoenix performed the first wet chemistry tests. On Sol 31, Phoenix returned the wet chemistry test results with information on the salts in the soil, and its acidity. The wet chemistry lab was part of the suite of tools called the Microscopy, Electrochemistry and Conductivity Analyzer. Preliminary wet chemistry lab results showed the surface soil is moderately alkaline, between penthouse 8 and 9. Magnesium, sodium, potassium and chloride ions were found. The overall level of salinity is modest. Chloride levels were low, and thus the bulk of the anions present were not initially identified. The pH and salinity level were viewed as benign from the standpoint of biology. TEGA analysis of its first soil sample indicated the presence of bound water and CO2 that were released during the final heating cycle. On August 1, 2008, Aviation Week reported that the White House has been alerted by NASA about plans to make an announcement soon on major new Phoenix lander discoveries concerning the potential for life on Mars, scientists tell Aviation Week and Space Technology. This led to a subdued media speculation on whether some evidence of past or present life had been discovered. To quell the speculation, NASA released preliminary and unconfirmed findings which suggest that Mars soil contains perchlorate and thus may not be as Earth-like and life-friendly as thought earlier. A 360-degree panorama assembled from images taken on Sols 1 and 3 after landing. The upper portion has been vertically stretched by a factor of 8 to bring out details. Visible near the horizon at full resolution are the backshell and parachute in the heat shield and its bounce mark. On the horizon, left of the weather mast, is a crater. End of the mission, the solar-powered lander operated 2 months longer than its 3-month prime mission. The lander was designed to last 90 days, and had been running on bonus time since the successful end of its primary mission in August 2008. On October 28, 2008, the spacecraft went into safe mode due to power constraints based on the insufficient amount of sunlight reaching the lander, as expected at this time of year. It was decided then to shut down the 4 heaters that keep the equipment warm, and upon bringing the spacecraft back from safe mode, commands were sent to turn off 2 of the heaters rather than only 1 as was originally planned for the first step. The heaters involved provide heat to the robotic arm, TEGA instrument and a pyrotechnic unit on the lander that were unused since landing, so these 3 instruments were also shut down. On November 10, Phoenix Mission Control reported the loss of contact with the Phoenix lander. The last signal was received on November 2. Immediately prior, Phoenix sent its final message, Triumph in binary code. The demise of the craft occurred as a result of a dust storm that reduced power generation even further. While the spacecraft's work ended, the analysis of data from the instruments was in its earliest stages. Communication attempts 2010, though it was not designed to survive the frigid Martian winter, the spacecraft's safe mode kept the option open to re-establish communications if the lander could have recharged its batteries during the next Martian spring. However, its landing location is in an area that is usually part of the North Polar ice cap during the Martian winter, and the lander was seen from orbit encased in dry ice. It is estimated that, at its peak, the layer of CO2 ice in the lander's vicinity would total about 30 grams per centimeter 2, which is enough to make a dense slab of dry ice at least 7A1 or 2 inches thick. It was considered unlikely that the spacecraft could endure this condition, as its fragile solar cell arrays would have cracked and fallen off since they were not designed to support much weight. Scientists attempted to make contact with Phoenix starting January 18, 2010, but were unsuccessful. Further attempts in February and April also failed to pick up any signal from the lander. Project manager Barry Goldstein announced on May 24, 2010 that the project was being formally ended. Images from the Mars Reconnaissance Orbiter showed that its solar panels were apparently irretrievably damaged by freezing during the Martian winter. Results of the mission, landscape. Unlike some other places visited on Mars with landers, nearly all the rocks near Phoenix are small. For about as far as the camera can see, the land is flat, but shaped into polygons between 2–3 meters in diameter and are bounded by troughs that are 20 cm to 50 cm deep. These shapes are due to ice in the soil expanding and contracting due to major temperature changes. The microscope showed that the soil on top of the polygons is composed of flat particles and rounded particles. Also, unlike other places visited on Mars, the site has no ripples or dunes. Ice is present a few inches below the surface in the middle of the polygons, and along its edges, the ice is at least 8 inches deep. When the ice is exposed to the Martian atmosphere, it slowly sublimates. Some dust devils were observed. Weather: snow was observed to fall from cirrus clouds. The clouds formed at a level in the atmosphere that was around a 65 degrees Celsius, so the clouds would have to be composed of water ice, rather than carbon dioxide ice because, at the low pressure of the Martian atmosphere, the temperature for forming carbon dioxide ice is much lower, less than a 120 degrees Celsius. As a result of the mission, it is now believed that water ice would have accumulated later in the year at this location. This represents a milestone in understanding Martian weather. Wind speeds ranged from 11 to 58 km per hour. The usual average speed was 36 km per hour. These speeds seem high, but the atmosphere of Mars is very thin, less than 1% of the Earth's, and so did not exert much force on the spacecraft. The highest temperature measured during the mission was a 19.6 degrees Celsius, while the coldest was a 97.7 degrees Celsius. Climate cycles: interpretation of the data transmitted from the craft was published in the journal Science. As per the peer-reviewed data, the presence of water ice has been confirmed and that the site had a wetter and warmer climate in the recent past. Finding calcium carbonate in the Martian soil leads scientists to believe that the site had been wet or damp in the geological past. During seasonal or longer period diurnal cycles, water may have been present as thin films. The tilt or obliquity of Mars changes far more than the Earth. Hence times of higher humidity are probable. The data also confirms the presence of the chemical perchlorate. Perchlorate makes up a few tenths of a % of the soil samples. Perchlorate is used as food by some bacteria on Earth. Another paper claims that the previously detected snow could lead to a buildup of water ice. The reports leaves the question of presence of organic compounds open-ended, since heating the samples containing perchlorate would have broken down the organic material. Surface chemistry: results published in the journal Science after the mission ended reported that chloride, bicarbonate, magnesium, sodium, potassium, calcium, and possibly sulfate were detected in the samples. The pH was narrowed down to 7.7 plus or minus 0.5. Perchlorate, a strong oxidizer at elevated temperatures, was detected. This was a significant discovery as perchlorate has the potential of being used for rocket fuel and as a source of oxygen for future colonists. Under certain conditions, perchlorate can inhibit life. However, some microorganisms obtain energy from the substance. The chemical, when mixed with water, can greatly lower freezing point of water, in a manner similar to how salt is applied to roads to melt ice. So, perchlorate may be allowing small amounts of liquid water to form on the surface of Mars today. Gullies, which are common in certain areas of Mars, may have formed from perchlorate melting ice and causing water to erode soil on steep slopes. Perchlorates have also been detected at the landing site of the Curiosity rover, nearer equatorial Mars, suggesting a global distribution of these salts. Scientific payload: Phoenix carries improved versions of University of Arizona panoramic cameras and volatiles analysis instrument from the ill-fated Mars Polar Lander, as well as experiments that had been built for the cancelled Mars Surveyor 2001 lander, including a JPL trench-digging robot arm, a set of wet chemistry laboratories, and optical and atomic force microscopes. The science payload also includes a descent imager and a suite of meteorological instruments. Robotic Arm and Camera. The robotic arm is designed to extend 2.35 m from its base on the lander, and has the ability to dig down to 0.5 m below the surface. It took samples of dirt and ice that were analyzed by other instruments on the lander. The arm was designed and built for the Jet Propulsion Laboratory by Alliance Space Systems, LLC, in Pasadena, California. A rotating rasp tool located in the heel of the scoop was used to cut into the strong permafrost. Cuttings from the rasp were ejected into the heel of the scoop and transferred to the front for delivery to the instruments. The rasp tool, also called the Icy Soils Acquisition Device, was conceived of at the Jet Propulsion Laboratory. The flight version of the rasp was designed and built by Honeybee Robotics in Manhattan, NY. Commands were sent for the arm to be deployed on May 28, 2008, beginning with the pushing aside of a protective covering intended to serve as a redundant precaution against potential contamination of Martian subsoil by earthly life forms. The robotic arm camera attached to the robotic arm just above the scoop was able to take full-color pictures of the area, as well as verify the samples that the scoop returned, and examine the grains of the area where the robotic arm had just dug. The camera was made by the University of Arizona and Max Planck Institute for Solar System Research, Germany. Surface Stereo Imager. The Surface Stereo Imager was the primary camera on the spacecraft. It is a stereo camera that is described as a higher resolution upgrade of the imager used for Mars Pathfinder and the Mars Polar Lander. It took several stereo images of the Martian Arctic, and also used the Sun as a reference, to measure the atmospheric distortion of the Martian atmosphere due to dust, air and other features. The camera was provided by the University of Arizona in collaboration with the Max Planck Institute for Solar System Research. Thermal and Evolved Gas Analyzer. The Thermal and Evolved Gas Analyzer is a combination of a high-temperature furnace with a mass spectrometer. It was used to bake samples of Martian dust and determine its content. It has 8 ovens, each about the size of a large ballpoint pen, which were able to analyze one sample each, for a total of 8 separate samples. Team members measured how much water vapor and carbon dioxide gas were given off, how much water ice the samples contained, and what minerals are present that may have formed during a wetter, warmer past climate. The instrument also measured organic volatiles, such as methane, down to 10 ppb. TEGA was built by the University of Arizona and University of Texas at Dallas. On May 29, 2008, electrical tests indicated an intermittent short circuit in TEGA, resulting from a glitch in one of the 2 filaments responsible for ionizing volatiles. NASA worked around the problem by configuring the backup filament as the primary and vice versa. On June 11 the first of the 8 ovens was filled with the A soil sample after several tries to get the soil sample through the screen of TEGA. On June 17, it was announced that no water was found in this sample. However, since it had been exposed to the atmosphere for several days prior to entering the oven, any initial water ice it might have contained could have been lost via sublimation. Mars Descent Imager. The Mars Descent Imager was intended to take pictures of the landing site during the last 3 minutes of descent. As originally planned, it would have begun taking pictures after the Enrashal departed, about 8 km above the Martian soil. Before launch, testing of the assembled spacecraft uncovered a potential data corruption problem with an interface card that was designed to route MADI image data as well as data from various other parts of the spacecraft. The potential problem could occur if the interface card were to receive a MADI picture during a critical phase of the spacecraft's final descent, at which point data from the spacecraft's inertial measurement unit could have been lost. This data was critical to controlling the descent and landing. This was judged to be an unacceptable risk, and it was decided to not use MADI during the mission. As the flaw was discovered too late for repairs, the camera remained installed on Phoenix but it was not used to take pictures, nor was its built-in microphone used. MADI images had been intended to help pinpoint exactly where the lander has landed, and possibly help find potential science targets. It was also to be used to learn if the area where the lander lands is typical of the surrounding terrain. MADI was built by Malin Space Science Systems, and it is the lightest and most efficient camera ever to land on Mars. It would have used only 3 watts of power during the imaging process, less than most other space cameras. It had originally been designed and built to perform the same function on the Mars Surveyor 2001 lander mission. After that mission was cancelled, MADI spent several years in storage until it was deployed on the Phoenix lander. Microscopy, Electrochemistry. and Conductivity Analyzer. The Microscopy, Electrochemistry, and Conductivity Analyzer is an instrument package originally designed for the cancelled Mars Surveyor 2001 lander mission. It consists of a wet chemistry lab, optical and atomic force microscope, and a thermal and electrical conductivity probe. The Jet Propulsion Laboratory built MECA. A Swiss consortium led by the University of Neuchâtel contributed the atomic force microscope. Using MECA, researchers examined soil particles as small as 16 I1/4 m across. Additionally, they attempted to determine the chemical composition of water-soluble ions in the soil. They also measured electrical and thermal conductivity of soil particles using a probe on the robotic arm scoop. Sample wheel and translation stage. This instrument presents 6 of 69 sample holders to an opening in the MECA instrument to which the robotic arm delivers the samples and then brings the samples to the optical microscope and the atomic force microscope. Imperial College London provided the microscope sample substrates. Optical microscope. The optical microscope, designed by the University of Arizona, is capable of making images of the Martian regolith with a resolution of 256 pixels or more 16 micrometers pixel. The field of view of the microscope is a 2x2m sample holder to which the robotic arm delivers the sample. The sample is illuminated either by 9 red, green and blue LEDs or by 3 LEDs emitting ultraviolet light. The electronics for the readout of the CCD chip are shared with the robotic arm camera, which is an identical CCD chip. Atomic force microscope. The atomic force microscope has access to a small area of the sample delivered to the optical microscope. The instrument scans over the sample with one of 8 silicon crystal tips and measures the repulsion of the tip from the sample. The maximum resolution is 0.1 micrometers. It was designed by the University of Neuchâtel. Wet Chemistry Lab. The Wet Chemistry Lab sensor assembly and leaching solution were designed and built by Thermo Fisher Scientific. The WCL actuator assembly was designed and built by Stasis Research in Boulder, Colorado. Tufts University developed the reagent pellets, barium ISE, ASV electrodes, and performed the pre-flight characterization of the sensor array. The robotic arm scooped up some soil, put it in one of 4 wet chemistry lab cells, where water was added, and while stirring, an array of electrochemical sensors measured a dozen dissolved ions such as sodium, magnesium, calcium, and sulfate that have leached out from the soil into the water. This provided information on the biological compatibility of the soil, both for possible indigenous microbes and for possible future Earth visitors. Every wet chemistry cell has 26 chemical sensors and a temperature sensor. The polymer ion selective electrodes were able to determine the concentration of ions by measuring the change of electric potential within the sensor, which is separated from the wet chemistry cell by an ion selective membrane. The 2 gas-sensing electrodes for oxygen and carbon dioxide work on the same principle and are separated from the wet chemistry cell by a gas-permeable membrane. A gold microelectrode array is used for the cyclic voltammetry and anodic stripping voltammetry. Cyclic voltammetry is a method to study ions by applying a waveform of varying potential and measuring the current voltage curve. Anodic stripping voltammetry first deposits the metals onto the gold electrode with an applied potential. After the potential is reversed, the current is measured while the metals are stripped off the electrode. The first measurement indicated that the surface layer contained water-soluble salts and had a pH between 8 and 9. Additional tests on soil composition revealed the presence of perchlorate. Later publication of results in the journals Science and JGA reported that chloride, bicarbonate, magnesium, sodium, potassium, calcium, and possibly sulfate were detected in the samples. The pH was narrowed down to 7.7 plus or a €0.5. Further data analysis has indicated that the soil contains soluble sulfate at a minimum of 1.1% WTA% SO3 and provided a refined formulation of the soil. Thermal and electrical conductivity probe. The MECA contains a thermal and electrical conductivity probe. The TECP, designed by Decagon Devices, has 4 short fat probes and 1 port on the side of the housing that made the following measurements: Martian soil temperature, relative humidity, thermal conductivity, electrical conductivity, dielectric permittivity, wind speed, atmospheric temperature. 3 of the 4 probes have tiny heating elements and temperature sensors inside them. One probe uses internal heating elements to send out a pulse of heat, recording the time the pulse is sent and monitoring the rate at which the heat is dissipated away from the probe. Adjacent needles sense when the heat pulse arrives. The speed that the heat travels away from the probe as well as the speed that it travels between probes allows scientists to measure thermal conductivity, specific heat and thermal diffusivity. The probes also measured the dielectric permittivity and electrical conductivity, which can be used to calculate moisture and salinity of the regolith. Needles 1 and 2 work in conjunction to measure salts in the regolith, heat the soil to measure thermal properties of the regolith, and measure soil temperature. Needles 3 and 4 measure liquid water in the regolith. Needle 4 is a reference thermometer for needles 1 and 2. The TECP humidity sensor is a relative humidity sensor, so it must be coupled with a temperature sensor in order to measure absolute humidity. Both the relative humidity sensor and a temperature sensor are attached directly to the circuit board of the TECP and are, therefore, assumed to be at the same temperature. Meteorological Station. The Meteorological Station recorded the daily weather of Mars during the course of the Phoenix mission. It is equipped with a wind indicator and pressure and temperature sensors. The MET also contains a LIDAR device for sampling the number of dust particles in the air. It was designed in Canada by Optech and MDA, supported by the Canadian Space Agency. A team headed by York University oversaw the science operations of the station. The York University team includes contributions from the University of Alberta, University of Aarhus, Dalhousie University, Finnish Meteorological Institute, Optech, and the Geological Survey of Canada. Canadian maker MacDonald Dettwiler and Associates of Richmond, BC built the MET. The surface wind velocity, pressure and temperatures were also monitored over the mission and show the evolution of the atmosphere with time. To measure dust and ice contribution to the atmosphere, a LIDAR was employed. The LIDAR collected information about the time-dependent structure of the planetary boundary layer by investigating the vertical distribution of dust, ice, fog and clouds in the local atmosphere. There are 3 temperature sensors on the 1M vertical mast at heights of approximately 250, 500 and 1000 ohm above the lander deck. The sensors were referenced to a measurement of absolute temperature at the base of the mast. A pressure sensor built by Finnish Meteorological Institute is located in the Payload electronics box, which sits on the surface of the deck, and houses the acquisition electronics for the MET payload. The pressure and temperature sensors commenced operations on Sol 0 and operate continuously, sampling once every 2 seconds. The Telltale is a joint Canadian-Danish instrument which provides a course estimate of wind speed and direction. The speed is based on the amount of deflection from vertical that is observed, while the wind direction is provided by which way this deflection occurs. A mirror, located under the Telltale, and a calibration cross, above are employed to increase the accuracy of the measurement. Either the SSI or RAC cameras could make this measurement, though the former was typically used. Periodic observations both day and night aid in understanding the diurnal variability of wind at the Phoenix landing site. The wind speeds ranged from 11 km to 58 km per hour. The usual average speed was 36 km per hour. The vertical pointing LIDAR detects multiple types of backscattering, with the delay between laser pulse generation and the return of light scattered by atmospheric particles determining the altitude at which scattering occurs. Additional information was obtained from backscattered light at different wavelengths, and the Phoenix system transmitted both 532 nm and 1064 nm. Such wavelength dependence may make it possible to discriminate between ice and dust, and serve as an indicator of the effective particle size. The Phoenix LiDAR laser is a passive Q-switched ND, YAG laser with the dual wavelengths of 1064 nm and 532 nm. It operates at 100 Hz with a pulse width of 10 nanoseconds. The scattered light is received by two detectors that operate, and the green signal is collected in both analog and photon counting modes. The LIDAR was operated for the first time at noon on Sol 3, recording the first surface extraterrestrial atmospheric profile. This first profile indicated well-mixed dust in the first few kilometers of the atmosphere of Mars, where the planetary boundary layer was observed by a marked decrease in scattering signal. The contour plot shows the amount of dust as a function of time and altitude, with warmer colors indicating more dust, and cooler colors, indicating less dust. There is also an instrumentation effect of the laser warming up, causing the appearance of dust increasing with time. A layer at 3.5 km can be observed in the plot, which could be extra dust, or less likely given the time of Sol this was acquired, a low-altitude ice cloud. The image on the left shows the Li Dar laser operating on the surface of Mars, as observed by the SSI looking straight up. The laser is the vertical line. Overhead dust can be seen both moving in the background, as well as passing through the laser beam in the form of bright sparkles. The fact that the beam appears to terminate is the result of the extremely small angle at which the SSI is observing the laser. The laser device discovered snow falling from clouds. This was not known before the mission. It was also determined that cirrus clouds formed in the area. Phoenix DVD. Attached to the deck of the lander is the Phoenix DVD, compiled by the Planetary Society. The disc contains Visions of Mars, a multimedia collection of literature and art about the Red Planet. Works include the text of H. G. Wells' War of the Worlds, Percival Lowell's Mars as the Abode of Life with a map of his proposed canals, Ray Bradbury's The Martian Chronicles, and Kim Stanley Robinson's Green Mars. There are also messages directly addressed to future Martian visitors or settlers from, among others, Carl Sagan and Arthur C. Clarke. In 2006, the Planetary Society collected 250,000 names submitted through the Internet and placed them on the disk, which claims, on the front, to be the first library on Mars. This Phoenix DVD is similar to the Voyager Golden Record that was sent on the Voyager 1 and 2 missions. A Phoenix DVD is made of a special silica glass designed to withstand the Martian environment, lasting for hundreds of years on the surface while it awaits discoverers. The text just below the center of the disc reads, "See also." 2007 in space flight, 2008 in space flight, exploration of Mars, icebreaker life, a proposed lander, list of rocks on Mars, Martian summer, references. External links, image map of Mars. The following image map of the planet Mars has embedded links to geographical features in addition to the noted rover and lander locations. Click on the features and you will be taken to the corresponding article pages. North is at the top. Elevations, red, yellow, blue,